Generative AI models have mastered the synthesis of light and texture. They manipulate the digital canvas with such precision that human observation can no longer detect where reality ends and fabrication begins. For years, the defense against manipulated media relied on neural networks hunting for isolated pixel anomalies or compression artifacts. These black box detectors fail against modern models that generate continuous, artifact-free visual fields. This radar chart represents the VeriGraf interface. Discarding pixel checking, it acts as a forensic audit, evaluating media strictly by physical laws. When a synthetic image lacking physical consistency enters, the green geometry collapses, immediately identifying exactly which optical or spatial rules were violated. Securing objective digital media requires an audit of the underlying physics. We have to verify the structural integrity of the scene itself. Automated black box verdicts leave forensic experts blind to the underlying rationale. The solution requires a design principle called generative friction, integrating human domain knowledge directly into the forensic loop. This interface features manual override sliders for variables like physics integrity and shadow vectors. Analysts use these to manually stress test the media's adherence to physical limits. Adjusting thresholds forces the system to recalculate dependencies, allowing operators to pinpoint the exact mathematical violations masked inside. This forensic architecture is the Cesare Protocol. It operates on version 2.1 of the Visual Integrity Truth Algorithm, or VITA-VQ. We establish trust through transparency. By forcing the algorithm to show its structural math to a human operator, the system remains verifiable at every level of analysis. The visual front-end is entirely dependent on the graph theory operating in the back-end. This graph visualizes dyadic reasoning. Traditional systems evaluate visual features in isolated one-to-one connections, testing a single claim at a time. Under this model, an AI-generated face can achieve a passing score. If the individual textures of an eye and a mouth register as highly realistic, they average out any synthetic inconsistencies elsewhere in the image. The system sees green across the board. Averaging isolated features fails to capture the true complexity of physical reality. The protocol corrects this by implementing a polyadic hypergraph. Rather than mapping single edges between 2 points, a hypergraph simultaneously encapsulates multiple features into a single structure known as a visual ensemble. A single hyperedge might contain the direction of a light source, the geometry of a cached shadow, and the photoresponse non-uniformity, the specific hardware noise of a camera sensor. These elements are bound by a holonomic constraint. They must mathematically coexist, according to the laws of optics and physical hardware. If generative interpolation causes even one node within this constraint to fail, it shatters the entire ensemble. A mechanism called the self-correcting delta transformer immediately detects this topological break, mathematically annihilating the compromised hyperedge from the record. You cannot average out a violation of physics. Verification requires the simultaneous, high-dimensional consistency that polyadic reasoning demands. Mapping the data is only the first step. The system must actively test the physics within that hypergraph. The environment executing these tests is the Predictive Action Orchestrator, or PAO. The PAO discards static diffusion step analysis. It relies on flow matching, utilizing continuous ordinary differential equations to measure the lawful generative flow of real-world imagery. This vector field illustrates a process called retrodiction. The PAO runs a backward simulation, mapping the continuous paths light must travel from a central source toward an object to verify it obeys the inverse square law. When the generated light transport violates the lighting plane or local gravity, the simulation clashes. The system registers the physical impossibility and issues a direct Lagrange multiplier penalty. Generative AI models construct excellent static pixels, but they cannot simulate continuous physical trajectories without triggering the orchestrator's constraints. Securing objective media means expanding these topological tests beyond static images. The protocol scales its physical verification directly into the acoustic domain. This extension is the Integrity Truth Audio layer. Instead of tracking photons and lighting vectors, the audio layer measures the structural continuity of sound over time, its mathematical persistence. This 3D scatter plot shows the extraction of 40-dimensional audio features, known as MFCCs. We map these features to form a continuous spatial ribbon, tracking acoustic structure frame by frame. The system deploys topological data analysis as a forensic scanner directly across this acoustic manifold. The scan looks for discontinuities. Structural tears in the ribbon indicate impossible physical jumps, the exact signature of audio splicing or generated speech elements. The system quantifies these topological anomalies as a persistence deviation score, routing the data straight back into the primary 9-pillar hypergraph. An authentic recording is an unbroken physical event. Light and sound flow continuously, and the forensic process must map that exact continuity against natural laws. The back-end physics simulations and the acoustic manifolds synthesize into a single conclusive output for the user. This is the equation for the veracity quotient. It defines exactly how the protocol establishes digital trust. The core variable is the weighted anomaly index. This subtracts the strict penalties identified across all 9 of the hypergraph structural pillars. The formula scales this index through the confidence penalty, adjusting for heavy compression or poor resolution, and the contextual variance, measuring external evidence like cryptographic provenance tags. We replace the opaque confidence percentages of traditional detectors with a cryptographically auditable, physically derived probability score. The Cesare Protocol derives its strict methodology from 4 decades of analog visual craft. It treats the capture of an image as a mechanical, physical truth. A photograph is an event. It is a specific arrangement of photons captured by specific hardware at a singular moment in time. As artificial intelligence maps the visual world with increasing fidelity, relying on isolated pixel analysis guarantees failure. The defense against fabricated reality requires structural transparency. It requires explicit tests of physical invariance, verified by human experts operating directly within the forensic loop. VITA-VQ enforces the boundaries of physics. It provides the scalable, deterministic framework necessary to ensure objective digital reality remains a measurable standard.